Okay. So we've got this idea about what x-intercepts are. You guys know what x-intercepts are, correct? Where your graph crosses the x-axis, right? Now we have different ways of describing them and talking about them. We have different words that we use and different notation. I want to make sure we're all kind of on the same page with that stuff. And also when I have x-intercepts, I should know factors of my polynomial. Okay, so that's something I'm kind of try to dive into today and analyze a little bit. Because if p is a polynomial function, c is called a zero. Okay, if p of c equals 0. Okay, so c is a 0 if p of p of c equals 0. All that's saying, guys. Okay, and basically what's happening here is this blue box here is what I think you should write, because it's reiterating what I've got up here written in text. But what this is saying is that we're choosing some x value, and we're calling it c. Okay? If p of c, so if you take c as an input into your function, and it spits back an output of 0, that means that that point is on the x-axis, isn't it? Okay? And if it's on the x-axis, it's intercepting the x-axis, right? Okay? So we have what we call an x-intercept. Or because it's producing a y value of 0, we call c a 0. Is that all right? Okay? Sometimes we call it a root as well. All right? But c is a 0. So here's the idea. If I have, I'm just going to jump back and forth between this and a specific on GeoGebra. Okay? What we're talking about here, if I look at these zeros on GeoGebra, the p of c that is producing 0, in this case would be p of -4 is giving me 0, right? So it tells me -4 is a 0. It's a numerical value. It's an x value that produces a y value of 0. What about p of -2? Is that a 0? Yeah. And p of 3 is also a 0. Okay? Because when I evaluate, and I'll show you this here, when you plug in, and I can type one in here. If I plug in and just ask this thing to evaluate f at -4, okay? So my function, maybe I'll rename my function here in a moment, but if I try f -4, to give me back a y value of 0, yeah. So it's running that -4 through here, doing all the algebra, adding things together, subtracting, that kind of stuff, and it gives me 0. Okay. See if I can rename this. So a lot of times they just use that capital P just to tell you that it, obviously stands for polynomial, right? Okay. But if if -4 is a 0, then -4, 0 is an x-intercept, right? Does that make sense? -2, 0 is an x-intercept. +3, 0 is an x-intercept, and that is what we're talking about down here in step number 4, actually. Okay. And these 1, 2, 3, 4s are all ways of saying the same thing, or they're called equivalent statements. Okay. So c is a 0 of p. X equals c is the solution of the equation. P of x equals 0. Okay. So if I set my equation, my function, replace p of x with 0, and then solve that, okay, c is going to be the value that pops up at the end that I solved for. Does that make sense? Okay. And the last one we have to talk about is that x minus c is a factor of p of x. If we go back to the specific case that we're using, okay, we would have the 3. So what we're getting here, when I look at this, is that if 3 is a 0, then x minus that is a factor of my polynomial p of x. Okay? If -2 is a 0, then x minus that is a factor of my polynomial. C is -4, and that's a 0, and x minus that is a factor of my polynomial, right? Okay. If I have a bunch of factors, we multiply factors together to get products, right? Well, think about this, okay? I'm going to tell you this is the least degree, this is the smallest degree polynomial we could have that shows this behavior. Do we know what degree that would be? Oops. Well, if it was 6, it would have to have in behavior that looked like that, right? Say again? Closer. It's 3. It's the third degree polynomial, okay? We have to, hopefully we know it's got to be odd. Because when it's odd, that's when the in behaviors are pointing in kind of opposite directions, right? If it was an even degree, the in behaviors would be both pointing up or they'd both be pointing down, okay? But if it's odd, one's going up, one's going down, okay? Now, so it's an odd degree. I told you it's the least odd degree, so 3, okay? Now, it could be 1, but you know if it's an odd degree of 1, it's linear, right? It's not linear. So it's a third degree polynomial. The in behavior here is showing me that if x gets to positive infinity, y goes to positive infinity, that automatically tells me my a coefficient has to be a positive number. Does that make sense? Okay. How do I get that polynomial? Well, polynomial is a product of factors. Do we now have our factors? Okay. So I'm going to type in real quick. Let's call it p sub 1 of x. And we will call it, or we'll write it as x plus 4 times x plus 2 times x minus 3. Okay? And it puts in there that, I think it's green right now, that green curve. It's not exactly what I wanted, right? It's not exactly what I had up there. Okay? Because if I hit enter on that, just for it is a green one, okay? What's the difference? Think about, now it's not expanded, but if you think about multiplying that out, FOIL out x plus 4, x plus 3, or so x plus 2, x minus 3. FOIL that, what is your first leading term going to be? X cubed, 1x cubed, right? What is p of x's leading term, leading coefficient? 0.31. Does that tell me what I need my a to be then? So I need to come out here in front and put a 0.31. And when I hit enter, does it give me that same curve? Okay? So that's kind of the way that we're going to work with understanding how to develop a third degree polynomial based off knowing what the factors are. Okay? I simply take my zeros, they turn into factors. Now I take my factors, I can multiply them together, and they should give me my product or my polynomial. Okay? Now if we can go that route, the idea is that it gives us an idea or gives us the ability to work in the other direction, okay? So I multiplied essentially these things together to get that, right? Our task most often is to start with what I have highlighted and get the green one, okay? Well, if I went from the green one to the highlighted one by multiplying, how do you think I'm going to go from the highlighted one to the green one? Changing order, right? Changing the direction that we went. So from one direction I multiplied. What do you think the other direction is going to incorporate? Dividing. Okay? And that's a fancy word for factoring. Right? Or factoring is a fancy word for dividing, correct? Okay? So our task, guys, eventually will be, they're going to tell you, you start with this. And I'm going to tell you that x plus 4 is a factor of it. You guys remember last year putting that underneath the divisor, or divisor bar, or whatever you call that, and putting x plus 4 out in front and going through the long division? When you do that long division, it's going to give you a quadratic up here. Okay? Well, that quadratic is going to produce those two zeros, okay, or those two other factors. So we're going to work through that process here eventually, okay, but that's kind of what our overall goal is to get to. So we can understand these zeros here. Now, I put that 0.31 out there. Let's just put A out there. Oh, I already had A. B. All right. Can you guys see that there's going to be an infinite number of cubics that have those same exact x-intercepts because of what we can do with transformations of stretching? So whenever they tell you that you have these particular x-intercepts and they ask you for a general equation, it could be any one of these, okay? If they ask me for a specific one, maybe they want me to come up with that one. In order to do that one, I need another point. We'll get to some examples of that. But does everybody understand the idea of x-intercepts and how they contribute to the polynomial, the structure of the polynomial? Here's another fact that can contribute to some of the work that we're going to be doing, and it's called the intermediate value theorem. Okay? It's pretty simple, but I want to make sure that we interpret it the correct way. So a lot of people will make mistakes or inaccurate arguments based on some results that you might get from this. Okay? So the intermediate value theorem for polynomials says if P is a polynomial function and P of A and P of B have opposite signs. Okay? Now P of A is simply just an x value. Okay? Some value on the x-axis that you've taken and you've plugged into your polynomial and you've evaluated. Okay? B is another x that is not A, different. And you've plugged in your polynomial, you've evaluated. Okay? If those two evaluated values come back and one is positive, one is negative, that tells you that there's an existence of a zero between those two x values. Okay? Now, it's an existence of at least one zero. There could be more, okay? But we know one has to occur, okay? And we should then be able to kind of maybe narrow our focus in on what potentially that could be, all right? And this is going to be we've seen this theorem being used by our calculators, by our Day3s or Day4s in the past. Maybe not thinking about it or knowing that this is what it was doing. But we've used this. Well, what's happening here, guys, is it's saying if I take P, just say, let's do it this way. Now, it's coming from a polynomial, okay? So it's key to know that there is a fact about polynomials that there are no breaks in them. There are no jumps, there's no holes, or anything like that. You may remember what that word is for polynomials? They're continuous, okay? So this is a fact for polynomials, meaning that my polynomial will not do something like this. It will not go, okay? Because there's a jump here, right? There's a gap. This is not continuous. What the intermediate value theorem is saying is if I have a point, let's say that I choose A to equal -3, okay? And I put that, and I evaluate, I run it through my polynomial, and it gives me that point right there. So let me call that P of lowercase a. All right, everybody? And what ultimately is going to use A to be -3, be P of -3. Okay? What's the Y value that I'm getting back there? 3. Okay? And really all I care about is that the Y value is positive, right? Okay. Let's then choose another x value. Let's call it B. Let's say B is equal to 2. And I plug that in. I evaluate. It gives me that point. So let's call that P of B, but it would be P of 2 if I was using a specific value. But what is the Y value that goes with that? -2. And really all I care about is that the Y value is negative. Okay? The Y value is negative, the Y value is positive. So if this is continuous, this is where we need continuity. Okay? Because if it was non-continuous, maybe my graph does something like this, okay? And if that were the case, then we do not cross the x-axis, right? Okay? But because it is continuous, we are guaranteed the existence of at least one zero. And when I go through that, and I got to go through P of B as well, what do I have to cross? I have to cross the x-axis. So it's telling me that somewhere in here is a C value that when I plug it into P, it produces 0. That makes sense, everybody? Okay. And then one of the tasks, our factoring is going to help us find that real quick, but one of the tasks is, okay, if I know A is equal to -3 and B was equal to 2, or sorry, positive 2, and there's a 0 in between them, I could start sliding that down and start sliding that down, evaluate again. See if I get a 0 on either of those. Does it make sense? Or still see if I get that positive, negative kind of attribute. Keep moving them in. And I can keep doing that, and we call it iterations. We keep doing the same thing over and over again with new values like this. And I can keep kind of sliding those in and evaluating. If I keep getting positive and negative, slide in a little bit further. Positive, still going to be negative. Slide in a little further, a little further, a little further. Eventually, what am I going to get? I'm going to get a 0. Okay? And that's the idea of the intermediate values here. Your calculator, like I said, our calculators, the Day3s, Day4s, have used this for us. I just got to make sure that this thing's still recording, guys. I didn't plug it in last night, so. All right. Sometimes when it just dies, it cancels out or stops the video too. So I don't know why the headphones do that, but it's weird. All right, so TI-8384. All I've got here is I went to y equals, I just put in some function, so some quadratic, and I want to find the zeros, okay? So I go second calc, okay, and I go down to 2. That's the 0, right? I'm looking for x-intercept of 0, this kind of equivalent statements, hit enter, okay? And now it asks me for what we call a left bound, okay? A left bound just means that I want to choose a ordered pair in which the x value is to the left of where I think my x-intercept is. Would you guys agree that that is to the left of where my first x-intercept is? Okay. So I'm going to hit enter. And so put in that little arrow there. Okay. I'll talk about what that does here in a moment. But now I ask for a right bound, so I'm going to go to the right of my x-intercept, right? I'm going to hit enter. And now I hope what you see here is because when I had a left bound, it was above the x-axis, right? When I chose a right bound, it was below the x-axis, okay? So what has to occur in between? Yeah, we got to have a 0. The intermediate value theorem is occurring here. Basically what your calculator is doing, when I hit enter the first time, it recorded that y value. Figured out what that y value was to that point. When I hit enter the second time, it figured out there's a y value down here. It knew if this y value is positive, that y value is negative. So if this thing, we know it's a polynomial, that's the only way that I was able to graph this thing. They know it's continuous. They know this goes from positive to negative. Somewhere in between, it has to hit a y value that is 0. So when I ask for yes, what it's doing is it's searching through all these ordered pairs between those two points. Okay, so it's choosing basically that a value and that b value that dictated those 2 points. Okay. And it's running through the infinite number of values between A and B, plugging them into my function, and seeing which one kicks back 0. Does that make sense? Okay. Now there's some more coding involved in that because you can't really necessarily do the infinite number of values. When you think about that, it would never get through the computing of that. But when I hit yes, it gives me my 0 of -3. Is that all right? So we've used that a little bit. Already, maybe last year, maybe the year before. That's what the intermediate value theorem is telling us. And that's a nice thing down the road when we start trying to graph these functions kind of comprehensively. Okay? Something that is going to be a task for us, like I said, is to graph comprehensive graphs. Okay? Now, we don't have enough calculus to get the best graph. But we got enough algebra under our belt to get a very, very, very good representation. Okay? The only thing that we're going to struggle with is finding maximum and minimum. Okay? And finding their precise locations on functions that are larger than quadratics. Okay? So third degree, fourth degree, fifth degree, we're going to struggle finding their max and minimum, the precise position of them. Okay? Because we don't have our calculus yet. When we're graphing these polynomials, okay, we're going to graph the zero. We're going to go find through the zero. Okay? Now, that part becomes difficult. Okay? Because when I want to find zeros, we kind of talked about it already. If I got this P of X, took it away from, let's go away. If I've got this P of X up here, that P of X, and I want to find the zeros of it, the way that I do that, the way the zeros show up is in that P sub 1 of X, right? In the factor form. That's how I want to get my zeros. So I need to be able to factor that top one to generate that green one. Okay? So our factoring skills are going to be kind of challenged as we go through this. And obviously, the higher the exponent, x to the third here, I have 3 factors, right? Because the only way that I can FOIL that out and get x to the third is having x times an x times an x at some stage, right? So I get 3 zeros. If it was x to the fourth, how many zeros do you think I'd have? Or how many factors I should say? Because how many factors I have might not be exactly how many zeros I have, but we'll get to that here in a little bit. But I should have 4 factors if it's x to the fourth. If I'm a fifth degree polynomial, how many factors should I have? 5, okay? So whatever my degree is tells me how many factors I should have, okay? So we've done quadratics. We've factored every quadratic we come across, and we've recognized that we get 2 factors in every one of them, okay? Now, some of them, the factors might repeat, but we get 2 of them, all right? So we can factor those. We can do that process. But third degree, fourth degree, fifth degree, is a little bit more difficult, okay? The hope is, though, as we're doing those third degree, fourth degree, fifth degree factoring processes, at some juncture in that process, we'll be able to use our quadratic factoring process, okay? You guys remember the rational root theorem last year? You probably remember as P over Q. Remember doing that kind of stuff? Okay. That is and it all goes with synthetic division, all goes with long division of polynomials, which synthetic division is just a shortcut for long division. That is the process of factoring polynomials. Okay. So we're going to rediscuss those things here in the near future. All right, so zero, so it says, find zero. Well, when they say that, that's easier said than done, and we'll work through that process. Test points, okay? These test points are taking the position of what calculus should do for us, all right? So next year, there'll be a juncture in calculus where you go through and do all this stuff again, okay? However, you should be much more efficient at it next year, okay, because your factoring skills will increase dramatically. And you shouldn't have to use test points. You'll have a calculus procedure that allows you to find your maximum minimum on the spot real quick, okay? But test points are going to take in account those maximum minimums. And that just means create a T-chart, essentially, choose some X values that are intelligent, evaluate, see what the Y values are, and plot a few test points between your intercepts, okay? Hidden behavior is going to be something we need. Okay, and hopefully that's something we can look at and realize right away. And then once we have those things, we just graph it, okay? All those things are going to be kind of meshed together as we work to take maybe a polynomial like that, and I ask you to graph it, okay? Now, let me show you, because I think it's important, we have time today, I think it's important to recognize that we don't have the ability right now, guys, to find those points E and F. Those are our maximums and minimums, right? Let me just get rid of that function. So E and F, I don't think F is on the right one. There we go. Okay, so finding those x values of those points is going to be very difficult for us right now, okay? We see that they're between our intercepts, though, right? Okay, so when they say in that step 2 of graphing that they try test points, we're going to find our zeros first. We're going to find -4, -2, and 3 first. And then it's going to be a good idea to say, okay, let's go. We had 2 zeros of -4, -2. Let's find some values in between us. So maybe I test -3. Maybe I test -2.5. Maybe I test -3.5. I get 3 test points in there, and it should then give me kind of how tall that maximum or that curve there should go between A and B. Does that make sense? Okay. And then I go, okay, well, I got -2 and 3 as x-intercepts. Now I'm going to try some test points between those. Maybe I try -1. Maybe I try, I already know 0, right? I already know my y-intercept. Maybe that's not a good one to choose because we've already got that math. But maybe I then try like an x value of 2. And I do my test values there and I plot those points. And that should help me find a good location for E and F. Okay? I want to show you, now I'm going to cheat a little bit because I have the solving system here for us to do this. But you'll learn that this is a pretty straightforward, easy process when you get to calculus, okay? Finding derivatives of what we call polynomials, okay? A derivative, basically, guys, is going to find us, it's an equation that's going to find us the slope of our curve at every single x value, okay? Think about our maximum minimums. We kind of already talked about this a couple weeks ago. Our maximum minimums, the slope of the tangent line, our maximum minimum, is going to be 0. And that's really nice because if I can kind of find an equation here of that P of x, the derivative of that P of x, okay? So, like I said, this does this kind of for me. But I'm going to write 0.31. I'm going to write it the factored way. It doesn't really matter how you do it. All right, so this is really easy algebra, guys. This is the way we do this. We take this number 3, and we multiply it by that number right there. So we can all do that multiplication, right? Okay, 0.93. And then we write x, and then we subtract 1 from that exponent. So it becomes 0.93 x squared. Okay? Then we go here, we do the same thing. So I take that 2, and I multiply it by 0.94. Whatever that gives me, then I write times x, and then I subtract 1 from my exponent, it gives me x to the first. And then that last one, I do the same thing. I take my exponent of 1 for the x, multiplied by the -3.13, and I get my derivative. So now my calculator is not going to show me maybe that derivative right away, okay? But let's see if I can get this to expand that. Let's go expand that. Gives me that. All right, so would you guys agree that 0.93 is 93 over 100? Okay, this number here, 0.94 times 2, okay, is going to be 93 over 50 if I change it to a fraction. And then would you guys agree that 3.13 times 1 is 31/10 as a fraction? I don't know why they use fraction. I don't know why they did. I guess because it's using the derivative process kind of purely. But that gives me that equation. Now, here's the nice thing about finding maximum minimum. That's a quadratic equation, right? Can you find the zeros of that quadratic equation? Can you use the quadratic formula for that? Ugly coefficients, but we should be able to say, I'll just say solve this equation equals 0 for x. If I solve that, it gives me this right there. Okay? Now, let's see if I can, I don't know if I can evaluate these. Let's just delete that out. Delete that out. Put that in. Hit enter. All right. Control C. All right, so I found the zeros of this thing, right? Now I'm going to see what that value actually is. I don't know why. Oh, yeah. There we go. So that value, get rid of this. That value is negative 0.308. Okay, if I highlight that, you can see that equation, or that value. Okay, and that's just the zero of what we call the derivative. Now let's look at E. See how E has the x value of negative 0.308? Okay, so that's how in calculus we will address kind of taking those test points out, not having to do test points. We'll do the derivative process. Okay, and it gives us those maximum minimums a lot easier, a lot quicker. And it boils down, guys, to doing what we're doing right now. Because when I have a cubic and I find its derivative, it gives me something squared, right? I can factor something squared. But if I have a fourth degree and I find its derivative is going to be the cubic. And we're going to learn how to factor cubics. And that's what we're going to get to. That's what we're trying to get ourselves an understanding for being able to do. If I have a fifth degree and I find its derivative, it's going to be a fourth degree. And I have to factor that fourth degree and find the maximum and minimum. Okay? So those are kind of the steps that are going to happen ahead of us in that course. And hopefully that opens your eyes then to how important learning how to factor right now and graph these curves right now is going to be for us. Because if we don't pick up on that algebra, we're going to struggle mightily with that calculus. All right, so we'll come back and we'll do some examples of this stuff. But I'm going to spend more of tomorrow doing just kind of pure examples of this. I want to get through and talk about one more relationship of functions that we're going to develop inside graphs that we can then just tomorrow just start seeing example after example after example and practice all these ideas. Okay, so it's the shape of the graph near a zero. Okay, you guys remember if I were to give you a function that looks like this. If I were to give you x plus 1 times x plus 1, okay? X plus 1, that's a quadratic, right? Plus 1 times x plus 1 quadratic. It's something squared. But here you have one factor that shows up twice, right? You'll have two factors, but they're the same one. You guys remember the behavior that we see there at that -1, at that x-intercept? Okay? It's tangent to it, right? Okay, you guys remember what you called -1 as an x-intercept last year? What word you used for it? If I factor a quadratic and I get one solution, but I get it 2 times, what's that called? You remember hearing the phrase double root? Okay, so that's a double root. Okay, if I have a triple root, that's a triple root. Okay, because the -1 is showing up 3 times. Let's look at this. Go x plus 1 again. Now I have a fourth, right? Okay, I have. Well, eventually we stop calling them double and triple, and we just say that they have a multiplicity of 4. Which means how many I have of them. Okay. Now here's my question. What are you going to see? Let's say I raise this to the nth power. And let's just change n from 1 to 12. Okay? So this exponent right here is 1, right? Okay, so that just kind of visualize what's going on there at that x-intercept of -1. If I make this thing, I messed my increments up. If I make this thing go to 2, still have an x-intercept at -1, right? Okay. What about 3? Still have an x-intercept there? What about 4? What about 5? 6, 7, 8, 9, 10, 11, 12, right? What are you seeing that happens when these are odd? Yeah, they're one. As we approach that x-intercept, we're approaching from kind of below the x-axis, right? We hit that x-intercept, and then we continue to travel through above the x-axis. Okay, so you pass through the x-axis. You continue to go and move in that direction as you have a multiplicity that is odd. If it's a multiplicity that is even, Fanny gave us this word a minute ago, if it's even, you just bump the x-axis at that x-intercept, right? So when I just bump it, it is, what's the word? Tangent. Tangent to the x-axis. It's only touching at one point. So what we end up with is this idea here, okay? It says, in general, if c is a 0 of p, and the corresponding factor x minus c occurs exactly m times, okay, in the factorization of p, then we say that c has a 0 of multiplicity m. What that means to me is if I go back and look at that -1, or the x plus 1 factor, it was raised to the second power, so I say it has a multiplicity of 2. Or it's raised to the third power, I say it has a multiplicity of 3. Does that make sense? However many times I see that factor showing up in my factored polynomial, I then dictate what it, and I discuss what multiplicity is. Why is that important? Once I know what the multiplicity is, if it's even or odd, I know now the behavior of the graph around that 0. Okay? So now we know in behavior, we now know zeros, and we know the behavior that a graph has or shows around a 0. Okay? So we're trying to kind of just fill in the critical parts of our function, critical parts of our graph, and eventually enough of those critical parts will give us a comprehensive graph. Okay? What they're saying here is that by considering test points on either side of the x-intercept, okay, we can determine whether we have tangency or if we pass through. And the idea here is if I have p of x, I'm just going to do one really easy one. If I do like x plus 1 and I square it, okay, so at -1, we should be tangent, right? Well, why does that happen? If I plug in -1.1 right here and add 1 to it, I get -0.1, right? -0.1 squared is 1/100, and it's positive. Does that make sense? Okay. So to the left of this, if I choose a value that's to the left of -1 here, I get a positive y value return. If I plug in a number that's to the right of -1, so -0.9, -0.9, plug it in here, you get 0.1, right? Okay. 0.1 squared is 1/100. Positive again, isn't it? So you see that onto the left-hand side of that -1, you're getting a positive y value. On the right-hand side, you're getting a positive y value. And then right at -1, you get a 0, right? So that shows you that you bump 0 and go back up. Okay, you have a tangency idea there. So, and the idea is, guys, if I square a negative, don't I always get positive? Okay, if I raise to the 4th power, don't I always get positive? What about 6th power, 8th power, right? I always get then positive. Now, I'm not saying that a 4th power is always going to be, that way. Okay, it could be a 4th power, it could be coming from the bottom, touch, and go down. Okay, because there could be a negative out front of. So if this was squared by a negative out front, okay, it's going to be concave down, but it's going to be tangent at -1 as well. That makes sense? Because that negative is going to take those y values that I evaluate here and just put them below. So every single time that we deal with multiplicities, okay, a multiplicity of 1, so a factor that shows up just one time, is going to be very kind of linear through our intercept. Okay, it's not linear, but it's very similar. Think about like this here. That c of -3. Okay, you see how it's very linear here, passing through. I were to zoom in far on that, what I see right there is a linear kind of behavior, right? Does that make sense? Okay. Now, if and I think I have to the way I've got this structure. Let's go x plus 2 to the 3rd, x minus 1. All right, so something like that. Okay. Do you see here? So this was so this function is x plus 2 to the 3rd. We have a multiplicity at -2 of 3, right? Okay. Do you see how when it's a odd multiplicity, that's a little bit bigger, or that is bigger than 1, okay? That it's not kind of a linear kind of passing through here at -2. Does that make sense? Okay? It's going to kind of look like this. It looks like an inverted S, okay? Every single time that I do that, let's say that I take that function, and instead of using 3, let's use 5. Does the behavior really change at all? No. If I use, 7 or 9, let's go 13. Odd still. Does the behavior really change at all? No. It just snugs up to the x-axis a little bit sooner. All right. But that S kind of shape is still there. And that's what this slide is getting at right here. Okay. If you have an odd multiplicity that is greater than 1, at that intercept, you're going to have that kind of inverted S. It's not going to pass through kind of in a very linear fashion, like we see with multiplicities of 1. Okay. There at the bottom it says you have an even multiplicity, okay, that is greater than 1, so squared, fourth, that kind of thing. You have that tendency, and the higher that power gets for when it's even, it's just going to kind of square off the base of that curve. Does that make sense? Okay. These are all behaviors, guys, that we have to understand and have to be able to recognize when I give you this polynomial. When I give you p of x equals x to the 4th, x minus 2 cubed, x plus 1 squared, okay? We need to understand that that is x to the 4th, x to the 3rd, x to the 2nd. So there is, what, 9 factors to this, right? Does that make sense? This is a 9th degree polynomial, all right? If I were to rewrite this maybe in a lengthy, maybe somewhat unintelligent way, and I ask you, what are your zeros? Are all of those things being multiplied together? Okay, so can we use that idea that if all of those multiply together and my product is 0, then one of them or all of them have to be 0? Okay, so could I say that this one here has to be 0, that one there has to be 0, that one there has to be 0, that one there has to be 0, right? X has to be 0 4 times. It's a multiplicity of 0. Okay, it's a multiplicity of 4 for that x-intercept or that 0 of 0. Okay, the x minus 2, it's a multiplicity of 3 times, right? It's a multiplicity of 3. And the x plus 1 is a multiplicity of 2. So when we get to graphing these, okay, here's the thing. All right, we know, and I'm not going to do any multiplication here, but if I multiply all that out, is that a positive x to the 9th? And hopefully that's something we can kind of argue and judge relatively quickly. So this thing is going to have, I'll just quickly graph it, it has in behavior like that. Okay? I know that it has a 0 at 0. So I'm going to put that 0 in. Okay? Now I'm going to put, just to remind myself, multiplicity of 4. Okay? I have a 0 at 2. It's a multiplicity of 3, right? And I have a 0 at -1. And it has a multiplicity of 2. Now, if I'm graphing left to right, and I know my in behavior, from left to right, in behavior is this. My first x-intercept is going to be right there, correct? That's a multiplicity of 2, so do I keep passing through it? Nope, I bounce down, right? Got to be tangent. Okay? Now, if I bounce down, excuse me, if I bounce down, and I got to go back up through this, don't I have to turn at some point? So let's turn, and I get to that x-intercept of m equals 4, or multiplicity of 4. What's that tell me? Bounce back down, right? Okay? Even multiplicity tell you to come tangent. And I keep going. Now, I don't know how far down I'm going to go, but eventually I got to get back up through 2, right? And 2 is a multiplicity of 3. So do I pass through it or do I bounce off of it? pass through it. And now, because it's 3, we know it's going to have kind of that weird little S shape occurring there. Okay? Now, it's an ugly graph, and graphing on my tablet here stinks, but if I were to go to GeoGebra, you're going to see something eerily similar to that, and we did it very quickly. Does that make sense? Okay? Now, what's the hard part? Later, next week, they're going to give me that in expanded form. So I'm going to see the x to the 9th plus x to the 8th plus x to the 7th, whatever that coefficients are, and we'll work to turn it into that P of x. All right? I did extend that homework through, I think, Tuesday, but don't even worry. I don't think we'll have maybe enough to talk about by Tuesday to finish that up. So right now, Tuesday, but that's probably just tentative.
Have a good day, Mr.
Thank you, too.